All right, so the first thing we're going to look at here are just radicals. Okay, so right here, the way that this radical is represented here is it's the square root of a. Okay, we're going to start with square roots, but we'll extend it to some other roots as well. But this is the radical. Okay, in the corner of your radical symbol is going to be an index. Okay, in this particular case, for a square root, the index is the unwritten 2. Okay, it might be written with some letter, or not letter, but some number, like a cube root or fourth root, and that's called the index. Okay, also, the number inside your radical might have some power to it. Okay, the number in the radical is called a radicand. I'll generally refer to it as a base. Okay, so this is a base, a to the m, and the index is the n value. Okay, and so keep in mind what the radical means. Okay, the radical as a whole represents the value that you can take to the power of your index to equal the radicand, the number that's inside the radical. So if I gave you the square root of 9, what value can you take to the power of this unwritten index, which again in a square root is what number? 2. What number can you take to the power of 2 to equal the number inside our radical, 9? 3 or negative 3, right? Okay, so that is what a radical is. So our answer to this would be 3. And now, when you are simplifying a radical by itself, you use the principal square root. Okay, so it's just the positive 3. It's not the negative. And the only time you're going to use the negative as well is if you're solving an equation where you extract a root to get your equation. So if I had something like this where it said x squared is equal to 9, and I was using the process of extracting a root to solve for x, now I have to take into consideration the positive and negative root. Okay, but if you're just looking to reduce or simplify your number, then you do not use the negative version, only the positive version. Okay, so it's only the principal square root. Okay, now, the other thing to keep in mind with respect to roots, and we're going to start mostly with square roots, is something to this effect. Okay, I want you to just think, you can write it down, or you just can imagine, what is the solution to this? The square root of the quantity 9 plus 16. So just take a moment, think about it. Okay, when you are working with radicals, okay, the radical, and we'll talk later about how it relates to a rational power, but a radical has the same sort of priority in order of operations as exponents. Okay, so it's very early on. Okay, but when you look at this here, you're taking the square root of this quantity 9 plus 16. Okay, so the square roots and radicals don't, what you guys would tend to refer as distribute through a sum. So this is not the square root of 9 plus the square root of 16. This is the square root of the sum of 9 and 16. So the way that you would solve this is you take the sum of 9 and 16, which is 25, and the square root of 25 is 5. And so that would be your simplified form. Okay? And students tend to make that mistake where they look at it as 3 plus 4 equals 7 a lot. So if you made that mistake, you're not alone. Okay, but do understand that the order of operations is intact here, and you would combine your quantity first and then apply the root to the whole sum. All right, so let's go through the two rules for radicals that we're going to apply in this section. The first has to do with a product rule. The product rule states the following. If you have the product of two factors inside a root, so here the square root of a times b, okay, that can simplify out into each individual factor, a and b, having the radical applied to it independently. So and these work in both directions. And you can go from right to left or left to right. Okay, so you might see it first and foremost in something like this when you're simplifying radicals. So the square root of 50. Okay, what you would look to do, would be going from left to right here. The square root of 50, you would look for factors of the number that are perfect squares or perfect powers of whatever the index is. And so when you would look at this, you would think of this as 25 times 2. And then you would apply the radical independently to each factor. So root 25 times root 2. And that would give you your simplified answer, which is the square root of 25, or 5 root 2. Now, hopefully you don't have to go through each of those individual steps. At this point, you should be able to look at it and kind of get through that whole process pretty seamlessly. Okay, and so I want you to try. I'm going to make it a little bit tougher by adding some variables in here. And so see if you can simplify this expression. Right. So when you are simplifying a radical in this form, what you're looking for is you're looking to basically remove perfect square factors out of the radical, leave factors that can't be simplified any further in the radical. So if you ever see me go through an example of it, I'm going to split it. I'm going to put a radical part, and I'm going to leave a part out of the radical. So when I look at my first number, 72, are there any perfect square factors you can remove from 72? Right, so you think of this as 36 times 2. So the square root of 36 comes out as a 6. The factor of 2 stays inside. And next I'm going to move, just kind of go down the line in that radical. So next I go to a to the 4th. You're looking for these powers, breaking this down into perfect powers of whatever the index is. So a to the 4th can be thought of as a squared times a squared. Okay? Each of those comes out as a what? The square root of a squared is a. The square root of a squared is a. So those come out as a squared. Now the way that you're going to hear me describe this process is when I simplify variable powers in radical, what I'm going to do is I'm going to look for powers of, or multiples of, whatever the index is. So from this power of 4, I'm looking for multiples of 2. How many multiples of 2 can I remove from 4? 2. So that comes out as a to the 2nd. When I remove 2 multiples of 2, or 2 sets of 2, which is 4, when I remove 4 from 4, how many a's are going to be left inside the radical? 4 from 4 leaves 0, so there's no a's left inside. Okay, so let me explain that, how I do it with the b's. So my index is a 2, so how many groups of 2 can I remove from 5? 2. Right? 2 groups of 2 is 4. If I remove 4 b's from inside, how many b's will I be left with? Just 1, and so that's what's left inside. And then this gives me my completely simplified form. We'll finish the notes on these, and if there's no access, I'll just continue with the notes. Okay, so the quotient rule is the other rule to keep in mind, and it's very similar to this, and that is if you have a fraction inside of a radical, then that radical can apply to both the numerator and denominator independently. So root a over root b can split off instead of working with the fraction as a whole. Okay, and again, where you might see this would be something like 7 over the square root of 7 over 25. Since 7 and 25 don't have any common factors to cancel or reduce, or since your denominator is a perfect square, you can simplify this into root 7 over root 25, which you can then simplify individually. Root 7 doesn't. Root 25 simplifies to the 5. Okay, and so once again, I want you to try this problem on your own. So if it's hard to see, I'll kind of read through it. But you have the square root of 9x to the 5th, y to the 14th, all over the square root of 3x to the 4th, y to the 5th. And I want you to see if you can simplify that. I mean, is it easier to reduce each one individually, or is it easier to group everything together and then try to reduce what you have? And because in this problem right here, the tendency might be to take the square root of 9, that's a perfect square, so you can simplify that. But if you do that, you wind up with a radical in the denominator. Okay, so the ideal way to approach this would be to go in the other direction. Take two individual radicals, combine it into one single radical. Right? And so if we combine these into one radical here, we have 9x to the 5th, y to the 14th, all over 3x to the 4th, y to the 5th. And if we were simplifying, 3 goes into 9, leaving a factor of 3. These 4 x's go into the numerator, leaving a power of 1. And these 5 y's go into the numerator, leaving a power of 9. Okay, and so what we wind up with here is the square root of 3x y to the 9th. And so we can simplify this and just move, just like we did over here, from the factor 3. Are there any perfect squares you can remove from 3? No, so that's going to stay inside the radical. What about how many groups of the index 2 can you remove from x to the 1st? None, so that leaves your x inside. And how many groups of 2 can we remove from y to the 9th? 4. 4 groups of 2 is 8, leaving how many y's inside? 1. And so that would be your simplified form.